Alright, in this video we're going to do a two-sample T confidence interval. And so we're going to compare Double Stuf Oreos to original Oreos. And you can see this by the two images I have at the bottom of the screen. And we're going to find out what is the difference between Nabisco Double Stuf Oreos compared to twice the original Oreos. So we'll go ahead and state the problem, define some of the variables. So what is the difference between Nabisco Double Stuf Oreos compared to twice the original Oreos? And in this case we're talking about just the stuffing. And if you notice here, we're going to go ahead and assign mu1 to the double stuff, the weight and the actual population, the mean population weight in grams of the white cream filling in each double stuff cookie, double stuff Oreo cookie. And mu2 is going to be the mean population weight in grams of the white cream filling in each original. So both are the white cream filling. So we're going to construct and interpret a 95% confidence interval for the difference in mean stuffing for the double stuff Oreos and twice the original Oreos. In terms of data collection, basically we just bought 4 packages of cookies. We emptied each of 2 packages of original Oreo cookies and 2 packages of double stuff Oreo cookies, laid them out on a desk to number them 1 to 36 for the original, 1 to 30 for the double stuff, and used random.org to select the random numbers for the 15 cookies in each package. It took too long in a period to just measure them all. So there, that picture shows one of my students and the random numbers they had generated from random.org. And then here that it shows them picking those cookies out of the lineup, basically. And so once they had their cookies picked, they went ahead and scraped the filling and place those filling pieces in cupcake papers. And you notice when you look at this, look at those cookies, those are the originals. If you've ever taken the stuffing off of an original Oreo, some of it sticks to the cookie, and so that causes a problem and changes our variance a little bit later on. How we weighed it, we used a pretty precise measure or scale in grams. This shows, I just threw a cookie in there just to take the picture, but it kind of shows you what we have. So we have 14.6 grams. I'm pretty sure that's an original cookie in there, in that paper. And it shows you that it's in a glass case that keeps you from blowing on it, keeps that thing pretty solid, and measures to the nearest thousandths of a gram. And here it shows my students going ahead and picking those things out and weighing them. So let's go back to the test. So are the samples random? In this case, students did randomly select 15 cookies from each package, although we realize that this is not a representative sample of all Oreo cookies, because not all cookies had an equal chance of being chosen. So the randomness part is pseudo-random. Can I say that? So is the sample independent? Sometimes it's called the 10% condition. Here we know that 15 is way less than 10% of the entire population of regular Oreos and double stuff Oreos. So we're going to be able to find the standard deviation. And then finally, the last one is large counts condition. Both samples for the double stuff and the sample for the original were at least 30. So we will be safe using a two-sample T procedure. However, it is interesting to take a look at the box plots of the two samples because we had some pretty cool things happen. So let's go ahead and do the problem. We'll calculate the test statistic. So I used GeoGebra. Remember, sample 1, if you look up here, sample 1 was the double stuff right here. Sample 2 was the original, twice the original. And I'll show you the data here in just a second. But notice we have a mean for the double stuff of 6.7 and a mean for, This was the actual original, and I'll have to pull up a new one. So this was the original, not doubled. So that's the mean of your just original weight of your Oreos in grams. So here I went ahead and redid the data. And maybe now is a good time to just take a look at the data. So pulling this stuff apart, you notice we have double stuff right here, and these are all the weights of each cookie all the way to 30. Here's the original weights of the stuffing, and again I'm measuring the stuffing only, not the cookie itself, and so you can see each of those. And then here is twice the original. So if you take 2.87 times 2, you get 5.74. And I did just let it use C2 times 2. Used a formula to calculate that, so I didn't make any mistakes there. So when you analyze this data, you get a mean for the double stuff at basically 6.8, and a mean for the single at 6.41. with a standard deviation of 0.12 and 1.2 respectively. This is kind of interesting because if you look at the original data, this is pretty cool, and you go down, let me pull this up so we can take a look at it. If you go down here, this is the weight of an original stuffing. And if you look at these data points like 2.81, that's actually probably an extreme in the other direction, but most of these things are at 3. There's a 3.02, there's a 3.01, there's a 3.2, there's a 3.2. Most of them are right around 3.1, 3.2. There you jumped up to 3.5. So this 6.25, my students thought that they messed up there, and they might have grabbed a double stuff on accident, because if you look at all the double stuffing, they're all right in the 6. Actually that 6.25 is a little light, and so that makes me think that something else happened where it's 6.25. But anyway, that is probably a potential outlier just in the data. And so what we do, and that's what creates that variance that's so big. So what we do here, this is the formula for confidence interval. So x1 minus x2, well, here's x bar 1, so the mean of sample 1, that goes here. The mean of sample 2, that goes here. T value, again, this video is not going to do that for you. I'm just going to show you how to do it with technology, but it's good just to see the formula. Standard deviation, we're going to square that to get the variance. So we're going to take that 0.1248, square it. That's going to go there. N1's 30. We have that. N2 is also 30. We have that. And then again for S2 squared, we're going to take that 1.2268 and square it for that position. So that's how you would calculate your confidence interval by hand. I wouldn't suggest doing that if you have technology available, because it'll do the formulas for you and it'll make fewer mistakes than you make, because I've noticed I make a few mistakes. So let's go ahead and start with GeoGebra, and I'm going to highlight the data. I'm going to go in here, hit this button, hit multivariable analysis, and I'll show you what happens. And you notice here is the box plot for the double stuff. Here is the box plot for the original, twice the original. And notice there's that 12 where I doubled that one. That was way out there. But notice even in the double stuff we had 2 outliers, one on the low end, one on the high end. And then if you want to calculate the statistics, you hit this button right here, and what you end up with is down below, and I'll move this so we can see it. Whoops. There we go. Now you can kind of see it's at the bottom of the screen. That's all your statistics, but we want to do a t-estimate difference of means. And there it is. So your margin of error is 0.46. Your lower limit is negative 0.115. Your upper limit is 0.805. Your standard error is 0.225, and your degrees of freedom are 29.6. So that gives you all the stats we need to complete the test. Now that's not the only way you can do this. If you have you can do it by hand, but also if you have a ti-nspire, here's the other one, and let's say we want to go ahead and graph these double. This would be this one here, all this column, that's the weight of the cream of the double stuff in grams. Here's twice the weight of the original in grams. And so if you go to home and we go over to notice I'm flipping back and forth. We're going to go ahead and go to data and statistics. We're going to add a chart basically. And down here at the bottom, you can scroll down to this, click on it, and we want, say we want the double stuff. Okay, there's your dot plot. You hit menu, plot type, and you could look at the box plot. And it shows you those two outliers also. Maybe you want a histogram. Oops, plot type, histogram, there it is. Or maybe you want a normal probability plot or normal quintile plot. Man, notice how that follows a straight line really nicely. Okay, maybe you don't want double, but you want to go to twice the regular. Okay, there's the data. Notice it doesn't follow as well because of this outlier right here. So let's take a look at the box plot. There it is, and it shows you that outlier pretty clearly. 12.58, double the original weight. It was 6 point something, 6.2 something. But anyway, that shows you that outlier. So that should be plenty to help you graph these to show in your normal, it's above 30, but it's always good to include some of the graphs for that. And so if you go back to the original data, let's go ahead and do a confidence interval in this. So you hit menu, you go to statistics, confidence interval, let me get to it. And we want a 2-sample t-interval. We want data. You could, if you had the stats, you could just plug in the stats, but we have the data entered, so why not? List 1 is double for x1. x2 or mu2 is twice the regular. We'll leave the frequencies alone. We want a 95% confidence interval. We are not going to pool the data. And we hit OK. And I've already done this, so here is my stuff. Oh, nope. Oh, there it is. There's my interval. I did a test earlier. So there's my interval. Oh, cancel. And then you just work your way down through all that. And so there's your lower limit, negative 0.115 to positive 0.805. And your mean difference and your margin of error, degrees of freedom, and all the way down through all the rest of it. And so now we're ready to go ahead and conclude. And so we are 95% confident that the interval from negative 0.115 grams to 0.805 grams of stuffing contains the true difference weight of double stuff and twice the weight of the original stuffing in Oreo cookies. Since 0 is contained in the interval, we have reason to believe that double stuffed Oreos contain twice the stuffing of original Oreos. And so there's our conclusion based on what our calculator or GeoGebra did for us. And hey, thanks Nabisco for creating a pretty cool problem.